Good morning, good afternoon, and good evening to all of our attendees joining us today for this latest Data Science Central webinar. This is Bill Voorhees, your host. I'm the Editorial Director for Data Science Central and also Chief Data Scientist for Data Magnum. I'd like to start off our event today by thanking Pivotal for sponsoring today's event. Pivotal is a longtime supporter of the Data Science Central community, and we're honored to have them sponsoring our event today. I'd also like to take this opportunity to mention and show our appreciation for some of our other recent sponsors, including Tableau, Microsoft, Hortonworks, Oracle, IBM, and Teradata, to name just a few. These past webinars are available on demand at datasciencecentral.com, and if you haven't had the opportunity to view them, I encourage you to take a look. They provide some very useful insight into a wide variety of topics that are of great interest to our data science community. Today's webinar is entitled, How Data Science is Preventing College Dropouts and Advancing Student Success. And before we begin, I'd like to briefly review the format for today's webinar. Today's event will be an hour long. We have one panelist that I'll introduce in just a minute. There will be a 10 to 15 minute Q&A following the presentation, and this event is being recorded and will be available on datasciencecentral.com in the next few days following today's live event. I'd also like to encourage all of our attendees to provide questions throughout the presentation. We'll be reviewing and presenting them on your behalf during the Q&A portion of today's event. So I'm very pleased to introduce today's speaker, Raghu Radhakrishnan. He is a principal data scientist with Pivotal, focused on IT security and fraud detection use cases. His background is in machine learning and signal processing. He helped customers realize business value from data that's stored on top of Pivotal's big data products. Now, Raghu received his PhD in electrical engineering from NYU, has authored a book on video summarization, published several journal and conference papers, and has several granted patents in the area of multimedia content analysis. Raghu, thanks for being with us today. We're looking forward to your presentation. You know, educational institutions have a wealth of data around student demographics, admissions, academic performance, and more. And in addition to these structured data sources, they also have unstructured data from sources such as student activity on academic discussion forums, campus network access, and ID card usage. And all of these data sources can be brought together in an institutional data lake to predict and influence student behavior, including attendance patterns, academic performance, and time to graduate. So in today's Data Science Central webinar, Raghu will discuss a recent collaborative project with a top university in which many data sources were used to build a 360-degree profile of student activity on campus and help predict student success. This session will also provide an overview of the data science pipelines that were developed for training and scoring multiple models in parallel in database. These pipelines are now being used to predict student metrics such as GPA, course grade, and time to graduate, and even as intervention tools to help prevent students from dropping out. So Raghu, with that, I'm going to turn it over to you. You can begin as soon as you're ready to go.
Good morning, everyone. Thank you, Bill. Thank you, everyone, for joining this webinar. Today, like Bill mentioned, we'll be talking about our recent experience with the top university in developing models to predict student success. This is joint work with my colleague, Srivatsan Ramanujan. Here is the agenda for today's talk. First, we would like to motivate what today's educators have as their top concerns to justify the cost of college education. And then we'll talk about how institutional data lake, what it is, and then how it actually can help address some of those concerns that these educators have. And then we will go over the typical data sources that can be brought into this institutional data lake, both structured and unstructured data sources. And we'll give you some examples along the way on what kind of features we extracted from these data sources to create a 360-degree view of the students And then using those features that we extract from these data sources, we actually developed 3 models to predict student success. The first one is a model to predict the time to graduate, whether he takes a normal 4 years to graduate or he's going to take more than 4 years to graduate for a particular student. And then we can also build a model to predict the term GPA and also the course grade for the student based on these features. And finally, we'll share some model operationalization pipelines that we developed for this top university. So today, the cost of education has been steeply increasing, and as a consequence, the student debt has also been increasing. And educators are concerned how to justify this value of college education and the cost, basically. And they worry about how they can ensure students graduate on time. If there is some way they can change some levers, introduce some policies, and provide some tools for the students so that they can graduate on time and they don't drop out and eventually get better jobs for their education at their universities. Now let's take a look at how an institutional data lake can help address these concerns. So before we, so what an institutional data lake is basically we bring together certain structured data sources that they've always had, like the demographics data related to admissions and the registration activity, things like that. And some of the unstructured data sources that we have access to are the online forum activity and activity in some learning management system like Blackboard. And we can also bring in card swipe activity that gives us information about what campus facilities are being used at what times. All these structured and unstructured data sources can be brought into a single place in a big data lake. And from these data sources, you start to look for certain student behaviors by analyzing this data. And we try to map those behaviors to certain student outcomes, like the time to graduate or the GPA. And once we can find a mapping using machine learning methods from these behaviors to the outcomes, then the educators can tweak some policies and tools to positively impact the student outcomes. So that's the idea behind building a institutional data lake to basically help the educators address their concerns and benefit the students in the long run. So once the data is in the institutional data lake, you can apply any type of analytics to address 2 things. One is to further education research. Basically, for example, you can predict the time to graduate or predict dropouts based on the student's activity in the first term itself. So it's not too late to act on it. And then the next thing is, based on these analytic models, you can push data-driven ads to the students on campus. For example, you can build a course recommender based on what kind of courses he or she has been taking over the course of time, and then help them specialize in a particular area. So we can push the analytics can help both the educators, education research, as well as help students along in their tenure at the school. So here is the problem statement we were after when we worked with this top university. So given the data related to a student's activity and their profile, we wanted to predict student success in terms of time to graduate. How quickly is he going to graduate? Is he going to take normal 4 years, or is he going to be late on graduation? And by developing a model, we basically wanted to identify key attributes that influence the dependent variable, here in this case, the time to graduate. And that will help the institution take action on some of those identified attributes. And we have to do this as early as the first term in which the student is enrolled. Basically, we look at what are the activities the student is doing in the first term, and then we are able to create a score for each student on the likelihood of him being late on graduation. And based on such a score, the university can act on those at-risk students brought out by our model. So our approach is to first create a 360-degree view of the student's activity and profile, and then apply machine learning methods to find a mapping between the features that we've extracted to the dependent variable, that is the time to graduate. And then after we develop the models, we interrogate the models to understand what factors are actually influential in predicting the dependent variable, and how the institute can intervene and help the students. Before I get into the actual method itself, I just wanted to give you an overview of the type of data science tools that are available on top of Pivotal's Big Data Suite and other products that we typically use when we work with customers. This is an eye chart which has a lot of products that helps the data scientist achieve the end goal. In the next slide, it will become clear how these products come together to build a model and deploy a data science-driven model, a data science-driven app. So as the data comes through, using Spring XD, you can ingest all the data into a data lake. And once the data is in, we can either use Hawk, which is Hadoop with query, or Pivotal's Greenplum database to interactively query the data and use it for munging with this big data framework in an interactive fashion. And once you have formulated the problem, then you can use a bunch of modeling tools that are available on top of Pivotal's big data products, both Greenplum database and Hawk, such as Madlib. Madlib is our library for scalable in-database machine learning. A lot of algorithms have been built on top of this, and we typically use many of the algorithms that are built in to train our models. Our platform is also flexible in that we can use the latest R and statistical packages in R and Python using the procedural languages, which we refer to as PLX, and also we have a Spark available on top of Pivotal Hadoop. Once the model is built, then we can use the trained model to score incoming data, and that can be consumed by an app that can be deployed on top of Pivotal's Cloud Foundry. I hope that kind of puts in place how these different Pivotal products come together in order to build a model and as well as deploy to an app that can be hosted on Cloud Foundry. So this is again more information on how our platform is flexible to let data scientists use the latest packages in Python or whatever language it may be, as long as the interpreter or the VM for language X is installed on each of the segment nodes or data nodes in the cluster. Then you're able to push computation to those nodes that are specified in terms of Python functions or R functions, and it works on each of the data that is available on each of the segments. I already talked about Madlib. The latest news is that Madlib is now open source and is part of Apache Software Foundation as an incubator project. and you could take a look and see how you can contribute as well. It has about 30 or more algorithms, both supervised and unsupervised. Many of the state-of-the-art machine learning algorithms are already available, and we are currently focusing on improving the usability, adding the basic metrics functions and things like that. So with that, let's come back to the problem at hand. So let's first take a look at what data sources were available in the institutional data lake and what kind of features we extracted from these data sources to create a 360-degree view of the student's activity and profile. So here it gives an overview of the different data sources. We had the data sources that are marked in orange, or structured data sources that are typically available for education research, that include applications related information, demographics, admissions related information, and also academic activity, including what courses they took and some registration related activity. And we also had information about their previous education profile, like the SAT scores, their performance from their high schools and things like that. So that constitutes all the registration, all the structured data sources, and the things that are indicated in green or unstructured data sources that we had access to, which includes the Blackboard activity. This is a learning management system where students can submit assignments online and have discussions online on forums about a particular course and things like that. We also had the students' network activity logs. This can tell us how students are or how active are students on the network, on their campus network. And we also had physical card swipes activity. We can look at when they were using various facilities, the dining facilities, laundry facilities, and the institutional facilities, things like that. Now, let's take a look at some of the interesting things that we could look at from the applications and admissions related data sources. Typically, we can compute things like admit rate and yield rate from these data sources. Admit rate is basically the ratio of number of applications that came into an university and how many were admitted per year. Typically, institutes like to look at these as a way to track how they are doing as an institution. And then we can also compute something called yield rate, which is the number of actual students who enrolled versus the number of students who actually got the admit. So these are two performance indicators for the university that you can compute from these data sources. We also looked at percentage of foreign applicants and percentage of residents. On the x-axis, you have term over term. What is the percentage of applicants that fall into these three categories? Foreign applicants, which is indicated in blue, and the number of percentage of applicants that are resident for that university, basically students applying from the same state, that is indicated in red. You can see that the percentage of residents for this particular university was going down, and the percentage of foreign applicants were going up over a period of time. Next, let's take a look at some of the academic activity related features. One example here is we looked at when do students take internships, when do students enroll for internship. The colors, different colors here, the color red shows the number of students who take internships in the fall semesters. The green shows the number of students who take internships in summer, and blue is for the spring semester. And this information is presented for a particular cohort, people who joined in fall 2008, and you can see that the number of students who take internships kind of peaks in the third year, and also people who take internships in the fall semester towards the end of their graduation. Fall 2012 is when the internships are highest for this cohort. And we saw similar behavior with other cohorts also. Then we looked into the changes in enrollment info, basically how many times a student change something about their major or program or college, and that would impact when they actually graduate. So you see a box plot of how many changes a student has made for different groups. The rightmost shows the number of changes made by a normal group of students, people who graduate on time, and the one that is shown in red is for the students who graduated late. And you can see that these students tend to change something about their program or major in the first 1 or 2 terms, and the later they make these changes, it can impact their time to graduate. We also had looked at this information for the group of students who dropped out, which is indicated in blue, and the color green represents students who did not drop out, but they are basically enrolled but not haven't graduated yet. So they are likely to be late, but we don't know more information about that. So we are going to track the features for these 4 groups of students as we go along and see how each feature provides value towards discriminating these 4 classes. We can also look at when they actually make these changes. There is some separation for these 4 classes when we look at when they actually make changes to their major or program or college. Now let's take a look at some of the other features that come from their previous education profile and some demographics. So here we are showing the box plot for their high school GPA. It's not surprising that people who don't do well in school also tend to drop out, as you can see in the box plot in the leftmost box plot shown in blue. There's also separation when we look at their school rank for these 4 classes. Oh, I forgot to mention that we found that female students tend to graduate on time, are more likely to graduate on time than male students. That's something we found from the demographics table as well. Now let's take a look at some of the unstructured data sources that we use to extract features. The first one is the from the learning management system that lets each student submit assignments online and have discussions about a topic for a course. So here the first feature, one of the interesting features that we extracted was to look at the percentage of assignments submitted by a student per course, and then we averaged that for the whole term for each of the students, and we looked at that quantity, and we found that students who drop out are less likely to submit all assignments in a course, which is not surprising. And there is some separation in this feature to predict the other classes as well. The next thing we looked at is how quickly do students submit their assignments. Do they wait until the last minute to submit the assignments? We were able to compute this quantity as well for all the assignments that are being submitted online in this learning management system, and that provides some weak signal between to discriminate these 4 classes. Then we looked at what is known as participation ratio. Basically, we looked at the ratio of number of posted messages to the number of viewed messages by each student. And this ratio is first of all always less than 1, which means all people view more messages than post messages. And what we find is that students who graduate on time tend to view most messages than they post. So that ratio is lowest for the normal students, and it's kind of high for the dropouts. They probably don't view as many messages, and they also probably post view fewer messages as well. So this kind of captures how they are participating in their online forums, on their course discussion boards and things like that. We also looked at how popular are these messages that are posted by these students, and what we find is that the median viewer count is largest for the messages posted by the normal grad, and also the message hit count provides some discrimination between these 4 categories that we were after. The next set of unstructured data that we looked at was trying to see what kind of how active the students were in the campus Wi-Fi network or internet, and we found that incomplete and late grads were using the network more than the others, maybe, and also in some cases we found they were active during the class itself, so which is not an ideal thing. We also looked at the card swipes activity in different locations and facilities within the campus. So what we found here was that the late grads are more likely to use laundry facilities while the classes are in session, similar to what we found in terms of network activity. And they were also, and we also found from the dining room facility access patterns, we found that the late grads were having their breakfast, lunch, and dinner later than normal on-time grads, which is kind of interesting. Now let's look at how we brought together all these different features that we extracted from various data sources to create these models. And for all these models, the independent variables came from all these features, that some of these examples that I just talked about. So in all, so I'd like to first introduce the 2 types of features that we had in our framework. For example, we had static features which remain the same irrespective of the time window we are looking at. For example, for a fall 2000 cohort, we define a window W1 which ends at the end of the first term, and then W2 which ends at the end of the second term, which is spring 2009. And for these 2 windows, static features such as gender, some previous education profile like their SAT score, some of the admission attributes, they don't change when we change these windows. So we have some of those static features that tell us what the student profile is. And on top of that, we had some time-sensitive features which depend on these windows W1 and W2, which is the first term or the second term. And from these windows, we extract their activity-based features, what they have been doing in the university in the first term or in the first 2 terms. We look at the network activity, the physical card access activity, what kind of courses they've been registering, and how their activity has been in their online forums. Some of the examples that we just saw from the different data sources, we are extracting such features, and at the end of each term, we can train a model and create a score for each student based on his activity and profile to say whether or not he's likely to graduate on time or not. Based on this information, the institute can now intervene and provide guidance to students who are at risk based on our model. So we extracted three, like I mentioned, we had the static features. We had 50 features of those type, and then we had about 115 time-sensitive features, and then we extracted about 110 features from the card swipes and the network logs. Basically, we were looking at the number of sessions each hour of the day and each day of the week. So these features were first extracted for the first term or the first two terms, and then we had these 4 groups of students, including people who graduated on time. Those are normal students who took less than 4 years, 3 or 4 years to graduate, and then people who graduated late, who took more than 4 years for their graduation, and people who dropped out before graduating, and then people who were incomplete. They didn't actually drop out, but they are still in the system but haven't enrolled back, so they are incomplete students. We had these 4 groups and these set of features, and we were able to build, using the same independent variables, we were able to build three different models. One is the time to graduate that I just described, and then we also built a model for predicting the course grade for each student, and the term GPA, because we are able to predict the course grade, then by predicting the course grade per course in a term, we can also predict the term GPA. We tried a bunch of different algorithms, including logistic regression, which is not an ensemble method, but the other 3 methods that we tried, AdaBoost and Random Forest from Scikit-learn, or ensemble methods, and then we tried something called Extreme Gradient Boost, which is a variant of AdaBoost, and it has been recently popular in all the Kaggle competitions in winning in getting the best performing model for a particular problem. So we tried all these 4 models for a problem at hand, and we found that the XGBoost model performed the best, and the Random Forest and AdaBoost were close second, and logistic regression, because it's not an ensemble model, did not perform as well. Now let's take a look at how we operationalize this framework that we built for the university. So on the left, you see the different structured and unstructured data sources, and using the feature generation code that is mainly SQL that's written on top of Greenfilm database or Pivotal Hawk, we extracted 3 groups of features: the static features, the time-sensitive features, and the cards and network logs based features. And we evaluated the value of these 3 groups of features. Basically, if we just use static features, then nothing would change from term 1 to term 2. But what we found is that bringing in these time-sensitive features that is based on what the student is actually doing in the first semester and the first 2 semesters had an impact on predicting whether or not they will graduate in time. So this shows that their not just their profile, which is static, that's important, but what they are actually doing on campus can help predict whether they are likely to graduate in time or not, and that information can be used by the university to intervene. And then after we extract these features, we use both scikit-learn and Madlib, which is on top of Greenplum database, to try out different modeling methods, both AdaBoost, Random Forest, and then XGBoost. We also implemented parallel grid search that we can do in database for searching for the parameters of the gradient boost method we tried. And once all the model parameters were serialized to disk after we have learned that, and for every week or every month, when we get new data about a student's activity on the Blackboard or network logs, then we can rerun the model on those new features that we extract from this recent data that came in, and come up with a list of at-risk students and their corresponding features that contributed towards their risk score, and that information can be examined by a data scientist or an analyst to see what kind of a message can be tailored to a particular student who's maybe consuming an app that the university has deployed, right? So the app can be used to contact students who are at risk and help them along in their tenure as a student at the school. So in this slide, I'm showing some information about how we implemented in database parallel grid search for finding the optimal parameters for the XGBoost algorithm using PL Python. We used PL Python as a driver function. To the way it was implemented is the training data set was basically converted into a pandas data frame and serialized, and then once the pandas data frame is serialized, it can be distributed to all the segments or data nodes in the Greenplum database. And then when we launch the grid search code, then it runs parallelly for each set of parameters in each of the segments. So the model learning is happening in parallel for each set of parameters, and so we can quickly find the optimal parameters for XGBoost in this way. And this information, we have shared this GitHub page where you can look at the details on how it has actually been implemented, and it's available for download as well there. That brings me to the conclusion. So we showed how we built an institutional data lake for our top university to serve as a platform for both educational research and for building data-driven apps for predicting student success and help the students along. And we reviewed various typical data sources that are available, both structured and unstructured data sources that are available on top of this institutional data lake that we built for the university. And we showed some interesting features that make up our student 360-degree view of both their activity and profile. And using some open source and scalable data science toolkits, we were able to build 3 different models using the same set of independent features to predict their time to graduate, their course grade for a particular term, and also their term GPA. And we set up a pipeline for operationalizing our models so that they can be consumed by a data-driven smartphone app that the university can then rely on to contact at-risk students and help them along as they may be at risk at dropout or at risk at graduating late. With that, I would like to pass it to Bill. These are some of the blogs that the Pivotal Data Science team frequently writes about many such use cases that we do with customers to help their particular use case on top of our platform. So you can take a look at this after when you have some time. Thank you. Thank you, Bill. Pass it over to you.
Raghu, thanks for that excellent presentation. It was really interesting. We'll get started with today's Q&A session, and I want to thank the audience for their participation. We've had a lot of questions that have come in during this presentation, and we'll do our best to get through all of them in the time remaining. So during this Q&A session, I'll leave up this screen, which has contact information for Raghu, if you'd like to contact him directly following today's webinar. So let's get started. Raghu, it appears that there are at least 3 different audiences on the college campus consuming this. There are obviously administrators and counselors and the students themselves. Can you give some examples of how they're consuming that and using that data, and whether or not their attitude toward these new scoring methods is pessimistic or accepting?
Yeah, thank you, Bill. That's a good question. So let me go to this slide to talk about the way the model is actually consumed. Like I mentioned earlier, we are looking at the students' activity in terms of what they are doing regarding the course, assignment submission, and things like that. So all these things are contributing towards whether they are likely to graduate in time or not. So let's say we deploy the time to graduate model as part of an app that can be downloaded by students on campus. Then what happens is, based on their activity, say every month, the administrators or the educators get a list of at-risk students whose activity is triggering the model to say that they are likely to graduate in time, not likely to graduate in time, and the administrator can then contact those students through the app and suggest some things that they can change about their behavior. They may say, okay, do you need any help to submit your assignments on time? Do you need some reading group? They may even suggest some social ways for them to form reading groups and help them along for their assignments, things like that. Hope that answers the question. Oh, the other part of the question is whether this was viewed as in a favorable way by the administrators. What we found was that the administrators really like this kind of output, because now they can intervene a student before it's too late, because these models are generating risk scores every month, so they're able to intervene earlier to help students that need help. So they view it favorably.
That's excellent. And did I hear you correctly saying that the models are run monthly, so that we can tell, say, within a term as opposed to between terms, whether or not a student is in trouble?
So when we delivered, we gave them the option. They are still figuring out at what scale they are going to run, time scale they are going to run at. We told them they could run every month or every term. It basically depends on how frequently they are refreshing their data lake with their recent activity.
Mm-hmm.
So that is to be seen. Mm-hmm.
I understand. Thank you. The audience is obviously very interested to know whether or not this model translates easily to other educational institutions. Do you think the features that you've identified are common amongst institutions, or is this something that needs to be heavily customized moving from school to school?
I think that's a very good question. There were many generic features like demographics and students' activity-related features. There are a fair number of features that are very common, I think, to many other institutions. That being said, there may be something that we can do to customize for each of the other institutions, depending on what data sources we have. Many of these data sources, I believe, are also available in other institutions. Maybe they have a different learning management system other than Blackboard. In that case, we'll have to look at that data source and bring some features to bear from the new data source that we see. But mostly, I would say 80% of the features should translate to other universities that are interested in doing such a thing.
Yeah, I bet that's true. Now, when you did this project, did you have a real wealth of historical data? Did you draw on a lot of historical data? And I guess the converse of that is, what happens if you don't have a lot of historical data to try and build this at another university?
Yeah, in this case, we had close to 7 years worth of data. That is how we were able to actually see, going back to fall 2008, we were able to see how long a particular student cohort is taking to graduate, right? In order to build a dependent variable, we needed to have a lot of history. We didn't use, we wanted to predict whether he is likely to graduate or not within the first 1 or 2 terms. So in that sense, even though we had a lot of history, we only used minimum information for it to be useful, right? We wanted to be able to predict just based on the activity in the first term or the first 2 terms as soon as possible.
I understand. About the project itself, can you tell us how long this project took to complete? And some of the members of the audience are interested about the number and types of data scientists that you used on the project. I think the issue is that they're surprised at the variety of skills that are necessary and wondering whether or not all the members of the team had all the skills, or whether or not you used specialized data scientists and leveraged the skills of the team.
Yeah, that's a good question as well. So we had 2 data scientists from Pivotal, that is Srivatsan, Watson, and myself. We worked with 2 data scientists from the university. They had 2 data scientists who were closely working with us. They were very familiar with the domain, what data sources, what they had some intuition for some of the features, and we knew the platform and Pivotal stack very well. So we initially we trained them on top of our platform on how to use our platform to do data science. And towards the end of it, actually, some of the models were actually built by their data scientists. We focused on the time to graduate model, and they took the same features and built the other 2 models, the course grade prediction and the time to grad and the term GPA prediction model were built by their own data scientists. So by the end of 3-month period, they were fully versed with our stack and how to run machine learning on top of our stack. And so it was a very enriching experience for us as well to work with them and learn the domain from them.
Excellent. Yeah, thank you very much for that observation. You know, I observed during your presentation that a lot of this work was done in Python. A lot of us are used to seeing more R. Can you talk to the issue of why you selected Python, and does the platform that you built support R?
That's a good question as well. So our platform supports both R and Python. It's just that both Watson and myself have a liking to Python, so we implemented many of the things in Python. But the R packages can be installed in each of the segments in Greenform database, and then you can write, you can invoke all those models using normal R code in each of the segments. I even implemented added boost in PLR for this engagement, but I didn't go down that very, because we found XGBoost to be performing well, which was available as a Python package. So that's why we decided to stick with Python. And but R is very much supported on top of our stack.
And of course, the audience wants to know, and perhaps you can't share specifics, but how close were your predictions to the rate of, for example, actual graduation or GPA or the other things that you were trying to predict?
Yeah, the university that we were working with for this, they didn't want to share the exact numbers, but it suffices to say that they were excited by looking at the numbers that we're getting, and that's why they are currently working on operationalizing this model. So we did get good accuracy in predicting late graduates based on their activity in the first term itself.
Well, it's exciting to know that this was successful. One of the things I expect you ran into were privacy issues. How were those raised and how were they addressed?
Yeah, that was one of the things that came up early on in the project when the data was being loaded. There were some federal regulations that we cannot see information, or so the data was basically anonymized before it was loaded into our environment. So that way we preserved the privacy of the student. That came up very early on when we actually talked about bringing all the data sources into our data lake.
Yeah. And regarding specific techniques, one member of the audience asked whether or not you did any unsupervised clustering and were the clusters meaningful, and another audience member asked about social network analysis. I know you had limited time, but were those things you considered or looked at?
So unsupervised clustering was something we had done in an engagement prior to this actual engagement with the university. There they just wanted to see what are some consistent groups based on the features. There was no dependent variable at that time. So we just wanted to, we created this 360-degree profile of the students and then ran a clustering algorithm on top of it and discovered different behaviors of students who naturally came together as clusters, and then we were able to show some consistent behaviors, and then that's when we realized that these behaviors can be tied to outcomes that the university cares about, and build a model to map the behaviors to some outcomes. And with regard to social network analysis, we didn't have time to explore that, but I think that is an interesting angle because sometimes we can create a network based on how students are taking courses together, how they go to places together, and try to see if there is any correlation in terms of whether if a group performs well, then it's because of the nearest neighbors in that group. Things like that. We did brainstorm about those things, but didn't have time to implement that.
Right. Well, Raghu, thank you so much for telling us so much about this really exciting project applying data science to education, which I think is probably one of the first to exist. Those were great answers to some very good questions. So for those of you that asked questions that weren't answered today, we'll be sending all the unanswered questions to Raghu and the Pivotal team so they can follow up with you after today's webinar. I have just a few quick announcements. Please mark your calendars for November 24th, and that's our next Data Science Central webinar, Best Fit Engineering for SQL on Hadoop. And that's going to be sponsored by Teradata and Hortonworks. Also, Today's webinar will be available on demand for viewing later today, and you can find it on the home page of datasciencecentral.com in the webinar tab that's located at the top of the page. Well, this brings today's webinar to a close. I'd like to thank our audience for their attendance and thoughtful questions, and a special thanks again for Pivotal and their sponsorship, and our speaker today, Raghu Radhakrishnan, for his insight into today's topic. My name is Bill Voorhees. I'm very pleased to have been your host for today's event. I look forward to seeing you all again on November 24th. Have a great day.
Thank you.